Just by a show of hands, who here has encountered a multi-threading bug? That should be everyone, because if you've used a modern operating system in the last, well, you're here, so you probably have encountered one. So in this code, I have a laser pointer. Can you spot the bug? More importantly, could you spot this during code review? If you haven't noticed by now, this is a kind of a classic data race. We're using the resource before in a thread, and then we're initializing it after we've created the thread. If this was single-threaded code, we could detect this with the static analyzer today. Maybe it was a use before, use after free or something like that. We could detect it, and we'd like to do this for multi-threaded code as well in our static analyzer. So what's stopping us from doing this? The answer is actually many things, but chiefly the problem is kind of how the analyzer looks at things. So the analyzer will go through the code and it will build a graph of all the possible states of the program, variables, memory, so forth. And with threaded code, it'll often visit both the parent and the child thread. But the problem ends up being that it creates separate graphs for each of them. And our state is marooned on each thread. And we can't even begin to start enabling kind of those cross-thread analyses if we have just completely separate thread and no way to connect it. So how do we connect it? Well, first we want to just kind of do that initial step of just initially let's just bridge our thread together. Let's combine. Let's just be able to look at the code, and then eventually, we can move on to fancier things like deadlock detection or data race detection. So today we're just focusing on that initial step of modeling that thread creation, bringing that combining that parent-child state there. In the future, we can model thread joins and potentially thread interleaving. For this, we have some goals we want to keep in mind. First of all, we want existing checkers to just work. We don't want to break a bunch of things or make it incompatible. And secondly, we also want this to be portable. So if you have a machine that has a 42-bit character, that should be fine. Or if you don't have shared memory or whatever it looks like, it should also work. And then we're also we're restricting our scope. We're targeting traditional CPU threads. We're not going to target GPU memory models. They're like CUDA or any other kind of SIMT model. Those things, you have stronger invariants. You can build a better abstraction there. So we're just going to go for those CPU threads. So what happens now in the analyzer? What is our blocker? So we can take a look at what happens. All threads, more or less, look the same. We have some function that the thread will execute. We have some data that we can give to the thread to initialize it. Maybe we have some additional metadata to name the thread or have a handle to the thread. And we really care about that function in that data. So when the analyzer looks at this right now, analyzer has two steps. First, the analyzer, it'll see that this is a function call. And this Clang Static Analyzer is very aggressive about trying to inline these because it's a way to prune the state space. And this will fail because it doesn't have the definition for what a thread is. In many cases, it's not possible because you dynamically link against your threading library. And then after it fails to inline the function, it's going to try to pass it along to a bunch of checkers. And these checkers are what implement the analysis in the static analyzer. And none of the checkers that will work with function calls, they don't know what a thread creation event is, and they're not going to do anything. And so at the end, all of our state that we've put into this thread creation, it just escapes, and we just pretend it's you can think of it as going to a black hole. So our what do? We want to kind of make this not go into a black hole. So we want to basically just link our two things. And we have a very simple solution. We have our two separate graphs. What if we just merge them? That's our kind of our goal. And we have a pretty powerful tool where we can just we have our function that we're executing on the thread. We can just inline it. And then we've merged our graph. And now all of our state is unified and all the checkers will work without any modification. So kind of our first attempt to try to implement this is as a modeling checker, where we're going to implement it as a checker. We're not going to actually do any analysis, but we're going to kind of encapsulate all our platform-specific state and try to model it. And this works. We did p-threads because they're kind of the most common denominator. We go through, we extract all our arguments, and then we try to inline it, and then we run into a bit of a wall. Because it turns out that inlining, it's not really available to the checkers. It's kind of stuck in the core. And more importantly, checkers are not designed to kind of influence the control flow of the symbolic execution. So we need to kind of rethink it. So our first try is to just slap it into the core. We added a config flag so that you can opt in. And then it's kind of you just copy and paste the code from before. And then the question is, of course, where do you put the code? And we just put it where the checker would have evaluated. You have some kind of default call evaluation where you do that inlining step and then you try to dispatch on your checkers. So we're just going to put our code there. And we have, like where we were before, we have our kind of our thread function and our data, and now we need to inline it. We have to make a call expression because we inline function calls and we just have a function. But other than that, we've inlined it and it works. So we can test it. So how do we know that it actually works? So with lit, we can introspect the internal state of the analyzer. So we can see that it kind of got butchered a little, but you can see that we can have a trivial example to show that we actually inlined the code. And then we can, after this, we can kind of step up to some bigger examples. We can add some little bugs, and we can show that we're enabling existing checkers to detect these bugs across thread boundaries. And we tested this for use after freeze, null dereferences, taint analysis, most of the core Unix checks. And then kind of step two is we've done these little toy examples, and now we need to test it on real code. So first we tried it on memcached. It found a crash, but it was in our code, not in memcached, unfortunately. So we fixed the bug, and after that, we didn't find any more bugs testing on real world code. And so what did we find? We didn't really see a big difference. This is kind of a good sign. It means we didn't really lose results. We didn't see meaningful performance overhead, although there's a big caveat there. I didn't have time to properly characterize this, so there's probably some cliff somewhere that you can run into. But kind of in the common case, there's a negligible difference. And we did show that we can find real bugs. So we took LZ4, and in the thread pool code there, we removed a null pointer check and we inserted a null pointer during thread initialization, and it did find it. But generally speaking, this is not going to find that many interesting bugs in open source code because realistically, you're going to be looking at initialization, which is probably very easy to test, and you're probably going to run into it. But it's a good starting point, and there are definitely some cases in platforms where you will be able to find a lot of interesting things. And where do you want to go from this? Our kind of goal is to upstream this so that we have this kind of starting point for doing thread work, and then later we can have better analysis and more complicated checks. And we want to start writing, once we've upstreamed it, we want to start writing more multi-threaded checks, start modeling more, and kind of go from there and have that drive where we go with it, instead of trying to kind of bite off, let's do thread interleaving right away. That's kind of it. If you have any questions, I'll be happy to take them. And there's my contact info if you want to reach out.
Hello, thank you for the talk. I have a few questions. Let's start by, have you considered exposing the inlining or have the control flow, basically a way for checkers to influence the control flow? Have you explored that option?
That is an option. It's been considered before, but that would probably be a very lot amount of bike shedding and take many years before that would happen. Because that would be, I think you'd probably need a pretty big re-architecturing of the analyzer.
A second question is, do you think that the same technique could be applied to higher order functions like std-find or whatever library functions we may have that is currently not inlined, and I don't know, those functors or predicate functions, they may also have some bugs that could be inferred from the invocation itself, basically connecting the data to the function or the predicate. Do you think the same technique could be applied there?
Yeah, I think that would probably work.
Thank you.
One more question. So, do you think this could be like extended to other like threading models, let's say OpenMP, and you know?
So for OpenMP, that would be like a more higher level model. Probably you would probably build on top of it. But OpenMP has kind of additional challenges because there's a lot of generated code. But I don't see why it wouldn't work. And then for like, I know for like the message passing like MPI, there is some existing work on that.
Cool, thanks.